So last time we glued objects, microgluing. So an arc was an embedded curve considered up to homotopy with certain properties. And we noted that every curve is the unique composite of segments contained in the triangles of a chosen triangulation of the surface. Maybe I draw a picture again. So this is a foreground. Then a segment was something like this. And if I compose these two segments, I get a curve in the foreground. Another curve would be this curve, where this is one segment, say delta 2, and this is delta 1. And then to every arc, we sketched how to get a corresponding global section of the gentle sheaf, which we obtained by gluing. And the gluing was simply an iterated pushout along the segments. So for every if we have n segments, we needed to take n-1 pushouts in the category of lax sections. And this was done by associating with every segment a local section, a lax section. And this lax section was the p relative left hand extension. P, remember, is the Grothendieck construction of the sheaf. And G relative left hand extension of the Grothendieck construction of an object living in f of Gi. So this is a vertex. This was a very abstract definition, but you could draw a picture. And for instance, we had this picture on the board last time, where this was on the foreground. This was this picture denotes a lax section of the gentle sheaf. These three edges are coCartesian. This edge is not coCartesian. This is why it's not a global section and only a lax section. And here it had the value k goes to k via the identity. And then if you apply the fiber function, you get 0. If you apply pi 0, you get k. If you apply pi 1, you get k. And this is how you get this lax section, which is the relative count extension of this guy here. So it's the relative count extension of its value at the vertex. And these are the building blocks out of which you glue your global sections together. Maybe some comments. In the lecture on gentle algebras by Jan, we saw that there's a construction of these arcs in a representation theoretic language called homotopy strings and bands. And this language is quite different. In this homotopy strings and band language, the global sections are constructed as iterated extensions. And here they are constructed as iterated pushouts. So it's not so easy to translate one into the other. And this language, I feel like, has the advantage that the gluing is geometric on the surface in terms of loops, whereas the other one is potentially less so. Right. So, and what will we do today? Three things. First, we will talk about stop removal, which is the fancy symplectic term for changing the number of marked points. Secondly, we will talk about induction. And thirdly, I will give an outlook on perverse sheaves, which are the class of constructible sheaves on graphs. So let me begin with one. So choose. Let's choose an external edge and E of G. So G is a spanning graph of a surface. And then we define G prime by basically removing the edge from G. So for example, if G was this graph, with this being E, then G prime is simply this graph. Let's do this. Then we want to define, so if we're given F, constructible sheaf on G, define F prime from exit of G prime stable by, so let this be the vertex V incident to E. So we set f prime of V to be the fiber product of f of V over f of E and 0. This factor here being the restriction from f of E to f of E. So you're taking the full subcategory of f of V such that of sections at V such that the restriction at the edge vanishes. Prime of V, and then for V prime or V tilde not equal to V, you set f prime of V tilde equal to f of V, and similar for all edges f not equal to V, you have f prime of f equal to f. And then the restriction maps are the obvious maps. Then there's an easy lemma. Exists a fiber sequence unstable, where so you have global sections of f. Here you have f of E, and this is evaluation at E. Generally, whenever we have an edge of the ribbon graph, we can restrict global sections to the edge E. In terms of coCartesian sections, maybe I should briefly say this. So evaluation E corresponds to restricting coCartesian edges. Sections. Sections.
Work to remove the shadow.
Yes. Yeah, the shadow is quite easy. Sections. 2E. Right? A section is simply a map from exit of G into the Grothendieck construction, and we pull this back along the inclusion of E into exit of G, and the pullback along this inclusion defines you this functor. And then the fibers of this functor will be R gamma G prime F prime. And the proof is immediate. It's simply the fact that limits commute with limits. Yes, so this is maybe one, and then the second part of this. The proof of one is limits commute with limits. So it's kind of the way we defined it. It's formal consequence. So this means that if you want to remove an external edge, you can simply take the full subcategory. This is the full subcategory. Full subcategory. Full subcategory of global sections. Sections whose restriction at E vanishes. So you can kind of, for instance, this is not a global section, but it's a like section whose restriction here is 0. So it would also lie in the subcategory of like sections where which is the fiber of this one. And then second statement, second lemma. If F is gentle, so is F prime. So this means this is now maybe the statement with more mathematical content. The other one is kind of formal hardware theory. How do you see this? So we have, let's say E is invariant, and you have F of E is equal to functors from delta n minus 2 to D, where D was the notation for D perf of K. And then if you evaluate at E, this becomes if you get the map to D, and if you compute, which is simply factors from delta 0 to D, now there's switch boards again. There is a co-fiber sequence. Let's more do it like this. But so say this map and the restriction map from the vertex to the edge can be chosen to be pulled back along the inclusion of delta 0 into delta n minus 2, given by the inclusion of the vertex n minus 2. And so what you're looking at here, the fiber of this map are all functors out of delta n minus 2, which map the last vertex to 0. And this is not hard to see to be equivalent. So fiber is equivalent to functors from delta n minus 3 to d. For instance, you can argue using Khan extension that this is an equivalence of categories here to the full subcategory of that guy, which maps the last vertex to 0. I'm not sure if you can read it if I have the board like this. Maybe I'll switch it. Okay, and this is somehow the computation that f prime is gentle at the vertex. Of course, you have to also now compute the restriction maps, but this is an exercise. So compute the restriction maps in f prime. It's an exercise. That's the proof. And so what does this mean? This means that if we have the topological Fukaya category of a marked surface with a set of stops and remove marked points, the symplectic geometers call them stops. And let me maybe write this. So take S M as a marked surface. You choose an M in M. Then you have the topological Fukaya category of S M without M embeds fully faithfully in the topological Fukaya category of S M. And it's in fact the fiber of a map to D of E perfectly, where this is the global sections R gamma F, and this is the other one. Right, and so this is a fiber sequence. Typically in the symplectic literature, they describe such co-fiber sequences. So if using co-sheaves instead of sheaves, co-sheaves instead of sheaves, one has a similar co-fiber sequence. Co-fiber sequence. Look, this is for instance in the paper by Metropolitan Chender. Of course, for Fukaya surfaces, it was known for a longer time. Co-fiber sequence, and this is called stop removal. And let me illustrate this in an example. This fiber sequence. So we look at the annulus with two marked points. Our ribbon graph. Let me put the marked points here and here. This is our ribbon graph. Then this would be G. Then what is the global sections? R gamma G and F. We saw this is equivalent to the perfect derived category of the conic chord. And so this category is actually smooth and proper. And so what happens if you remove I don't know if yellow is okay. E1, E2. So let's say remove E1. Then you get a full subcategory, which in this case turns out to be the finite derived category of the polynomial algebra. So these are finite modules. Meaning they're perfect over the field. If you want. And then if you remove E2, So let's call this maybe A, and this is T. This is the same as invert T and invert A, invert A, and you invert T, and you get the full subcategory of finite modules with a Laurent curve. So those are the subcategories you get from here. And what are these are all, this is somehow the proper, these are all proper categories, meaning the derived forms are all finite dimensional. There's the smooth version of this, which is then a localization sequence. So you start with the same guy, curve. And then you can localize this to d curve of kt, which localizes to d curve k t plus minus. And so they will be the same, but they will not. The other ones will not be the same. And the reason that these are the same is because this category is smooth and proper. And the reason for that is that every boundary component has a stop, has a mark point. But as soon as you're here, when I'm removing E1, the interior circle will have no more marked points. And then there are two versions of the Fukaya category. So far, we've always been defining the proper version. Well, we've been in the setting with the proof is proper, smooth and proper on one side, so this has been fine. But then if you do the same limit construction, you get the proper version of the Fukaya category. And there's a dual version, which is the smooth one, and it's the perfect derived. And then instead of a subcategory, you get a quotient. So this is stop remove. Yeah, Christian.
Where does this word stop come from?
The stop.
Yeah.
So this has to do with the partial wrapping in the partial wrapped Fukaya category. So an object in the partial wrapped Fukaya category is an arc, is a Lagrangian subsurface, submanifold, and then you compute the hum by wrapping along the Reed flow at infinity. And in the partially wrapped Fukaya category, as opposed to the wrapped Fukaya category, you stop wrapping as soon as you hit a stop. And so to compute the hums, you do this so-called partial wrapping, and you do it partial until you hit the stop. This is where the phenomenology comes from.
And in this example, we get the fully wrapped, they call it, not the.
Yes, this is the wrapped. So this would be the fully wrapped. Wrapped category of T square epsilon, which is the angulus, and this would be the this would just be called the Fukaya category of T star plus 1, or the compact. Sometimes people call this the compact category, because the objects are then compact Lagrangians, which are just closed curves, if you want. So in general, there's if you have no stops, there are two versions of the Fukaya category. One is called the wrapped Fukaya category, where these objects correspond to submanifolds which are not necessarily compact. And there's a version where they are compact, and it's called the compact Fukaya category. This embeds in. Well, it's not equal.
So what does this finite?
So it's the module is finite
Yeah.
if its total homology is a perfect module over the field. So I am just saying I'm looking at DG modules, whose if I sum up all the homology degrees, I get a finite dimensional vector space. Some people call this PVD for perfectly valued. Okay. So let's talk about induction. And so the story about this is that we want to look at, so some of the upshot of lecture 2 and lecture 3 was that it doesn't matter which ribbon graph we choose, we can always do the same computation. And now the upshot of this discussion is that it matters which ribbon graph we choose, and it gives us new information. So a lot of things, it doesn't matter, but then choosing a ribbon graph actually tells you more, or there's specifies certain data. So we want to describe the adjoint of the factor evaluation from global sections at the left adjoint, global sections UF to f of b. And we denote this, denote it, induction left e f of b r gamma b. And so this is for any edge e. If the edge is an internal edge, of course, this functor only makes sense to write down for the specific ribbon graph. And not every edge is part of every ribbon graph, if someone doesn't make sense to Cosmic. And before I tell you how to describe this functor, there's one comment. So how did we must make an observation about this gluing that we did last time. Namely, if you remember, we have these three indecomposable objects in the A2 covariant. So if we look at factors from delta 1 to b, which contains the objects k goes to k, 0 goes to k, and k goes to 0. And we use these three objects to match with the three arcs in the triangle. The three segments as well. So, the arcs. Well, let's just hold them. And so our gluing includes these three pieces. These three pieces, in fact, they all come from one of the three edges of the triangle. Namely, this is something we computed in lecture. Is it 2? I think lecture 2. Namely, if you take f from E to EI, left the joint of k, this is equal to some Si shifted by some L, where I don't know what L is, 0 or 1. And this will be denoted by S1, this will be denoted by S0, and this will be denoted by S2. So let me do an example. If you take the fiber functor from functors of the one B, the left joint, what does it give you? It gives you k goes to 0. Is that right? Sure. So this would be S0. So it turns out, and this is somehow a crucial observation, that the three objects you assign to the triangle, they are more local than the triangle. They actually come from edges. I would call this induction from an edge to a triangle. Induction being the left adjoint of this restriction of sections. So now this has a formal consequence, which is the following.
So is it like turning right, you said?
Yes, okay. Yes, exactly. So if I have, let me maybe draw that. So if this is my edge E, then f of V E left adjoint will be this arc, which turns right. So now we just make a global version of this statement about turning right. We say let E be an edge of G. We define an arc gamma E right turning by starting at E and always turning right. Always turning right in both directions. So let me draw a picture. This will kind of make it clear. If this is your ribbon graph and this is E, then what is gamma E going right? It would start here. Then it would go like this, and it would also go in the other direction, go like this. And then let me add some more edge, some more vertices. Let's say forward vertex. And what you would do is you would just go right. Kind of easy description. And then the proposition is that induction left E of K is equivalent to the global section corresponding to the right turning curve. Let us attempt to prove this. Maybe first statement is that so it's not automatic that this is the left adjoint. Since we're not working with presentable categories, maybe the proposition is the adjoint exists and satisfies this formula. That would be a more precise way of saying this. Right. Where did I put the sheet? Sorry. Yeah.
Like curve is like a dual curve. I mean, like a dual arc.
Yes. Yes, in fact, it's just the dual of the the dual arc to the rim graph. Yes. Right. Absolutely. So for simplicity, let's say that gamma is composed of delta 2 and delta 1. So for instance, this just means essentially everyone is foregone, and then this would be vertex E1, E2, let's say this is E, this is an edge we call E prime, and then gamma would be this arc. Gamma. Then we modify gamma E. Right, this is the push out of L delta 1 E1 L delta 2 V2, and this is L E prime, which is defined by having value K at E prime and 0 else. Of course, instead of K, you may have a shift of K here. Let's pretend there are no shifts for notational simplicity. And this is the push out in lax sections, but actually this defines your global section. So it's in the full subcategory of lax sections in my competition global sections. Right. And so now to what we do is we take any global sections, global section, gamma GF, and we want to show that R hom from this is the derived hom from X gamma E right turning Y. This is equivalent to R hom in F of E from K to Y of E, which is simply Y of E. This would mean, if you show this factorially, this means that they're adjoint. The adjoint of evaluation, this is evaluation E of 1, is given by induction, and this takes this value. So now what do we do? So R hom, this is this functor is exact in both components. So this means that this push-out diagram here gets mapped to a pullback diagram if we plug it into the first component of R hom. So R hom from X gamma E right turning to Y will be the pullback of R hom L E1 delta 1 Y R hom L delta 2 V2 Y, and here we have R hom L E prime Y. So how do we? So this is an R hom in taking in global sections, and this is an R hom taking in local sections. Lax sections, sorry, and lax sections, and you can now kind of ask, how would I ever compute this? This sounds really complicated. I don't even know. This is a derived category of the general algebra. I know that how to compute forms in there in principle, but in lax sections, I don't have any presentation of that category in terms of a generator, say an algebra. But actually, these objects are defined using card extension, and this kind of saves us. So L, let's say V2 delta 2. This was the P relative time extension of L V2 delta 2 of V2. Time extension, remember, is defined as the left adjoint of restriction. Hence, this arham is simply the following. Arham L V2 delta 2 y is now equivalent to by time extension universal property relative time extension to the arham in f of v from L V2 delta 2 of V2 from to y of V2. And now we use this remark I make on this other board that that this adjoint here gives you the symbols which we use for the gluing. So this in turn is equivalent. This guy here is given by L F going from V2 to E prime left adjoint of K. This means, what does this mean? This means that the segment delta 2 turns right. This is where we're now using that the way we define this arc by always turning right. This means that at every vertex, the value is given by the value of some left adjoint functor of the previous edge. So here, this would be delta 2. This part, it turns right. And this means that the value at the vertex is given by the left adjoint of restriction to E prime. So once you use that, we can again use another adjunction, and we get the arham from f of E from K to y of E. Right. Y E prime. This is because y is a global section. This means that the value at E prime is obtained by restricting the value at V2. This is now we're using that y is a global section. And so this is equivalent to, or if you do a similar computation for this guy, arham L E prime y, again using time extension. So this guy now is left time extension at E prime. So you also get arham f of E from K to y of E prime. So what does this computation mean? It means that this map here is an equivalence. No, yeah, no. This map is an equivalence. So how do we compute the pullback? Well, it's just given by the upper right term. Arham x gamma e right turning to y is equivalent to arham from L V1 delta 1 y, which again, this is left hand extension. So we do the same computation again. This time we get the other edge. This time we get arham from K to y of E, which is simply y of E, which is what we wanted to show. Of course, if you have more arc segments here, the same proof somehow works. So if you take instead right induction instead of left induction, you get curves that always turn left. The proof follows by passing to the opposite category. And yeah. So this is why is this an interesting statement to describe these curves? Well, we now get a characterization of of when these functors, these induction functors, are fully faithful. Let me maybe keep this important notation. Sure, we need it again. So corollary. Let E be an external edge. Then induction, like E from f of E to global sections is fully faithful. If and only if the boundary component intersecting E has at least 2 mark points. These 2 marked points. And so the proof goes as follows. Take your ribbon graph with the, again, I need some color. Those are the stops. And so this is the surface. Can be whatever surface. Has some other boundary components potentially with marked points. And say this is E. And this right turning curve, what it gives you is simply this arc in the surface. This will be gamma E right turning. And so if we compute, we want to show fully faithfulness, we can prove that the unit is an equivalence or not. And we look at the transformation from the identity to evaluation at E of induction left at E. And so if you evaluate this at K you get evaluation of E of gamma X gamma right turning E. And so what is this? Now, if there are 2 mark points or more, say 3, then gamma E starts at E but ends somewhere else. And this is K for 2 greater equal than 2 mark points. And in the case that there's only one boundary component, mark point on the boundary component, if you look at this arc, the arc goes inside. If you look at this arc, this evaluates at the edge twice. So you would get K plus some shift of K. 1 mark point. Right. So and similarly, or maybe one comment in this remark, this localization sequence here, where is it? This fiber sequence also becomes a co-fiber sequence, because in that case the evaluation factor is a localization, because the edge joint is fully faithful. So for greater equal than 2 mark points, evaluation P is a localization, and get stop removal, fiber and co-fiber sequence. Maybe I should draw. Let's say we draw the ribbon graph here, and you always turn right. So if this is your ribbon graph, then the arc you get is literally this. And then maybe you see why it evaluates twice better. This picture is more convincing. Right, you start at the edge, then you turn turn right here, you turn right here, and you come back where you started. And this happens if and only if you have exactly 1 mark point. And then this is not equal to, so you would have the inclusion of K into either K or K plus L. and this is the unit. And you're fully faithful if you know the unit is an equivalent. And so for the other edges, you also get a characterization of when you're fully faithful. It's a bit more complicated to say exactly what it is, so I won't do it here. But with this, you can in principle then, under somewhat mild assumptions, iteratively decompose your derived category, the topological Fukaya category, into derived categories of the field. And with this, you can, for instance, compute additive invariants such as K-theory of topological Fukaya categories. And similar things have been done, for instance, in a paper by Tobias Dückerhoff on A1 and homotopy invariance of topological Fukaya categories. How much more time do I have?
About 15 minutes.
Yes. So now, I will try to tell you what a perverse Schober is in the way that I've never done before, because it's kind of an interesting angle to explain this. Basically, perverse Schober, you can say, is a constructible sheaf where the same theorem for induction still holds true. This is not how it's up. So perverse Schobers, the notion that there is such a notion was proposed by Kapranov and Schechtman. A Schober is a German word. It means haystack. So a Schober is a sheaf of categories, stable categories, let's say. So our constructible sheaves of stable infinity categories, they are Schobers. And then what is perverse? Well, it has to do with perverse sheaves, but let's not get into this in 15 minutes. So that maybe I'll just give the definition of and then we'll kind of see what this means. So let n bigger equal than 2. A perverse Schober on the n spider consists of a collection of functors fi from en to ni, where 1 is less equal than I is equal than n, such that 1, there are junctions secondly, GI is fully faithful. Thirdly, so this is by the way the same as fi GI, right? If you take the co-unit, you get the identity at ni. Then fi composed with GI plus 1 is an equivalence of infinity categories. Fj composed with Gj is 0 if fi composed with Gj, if j is not equal to I or I plus 1. And lastly, for the fiber of h I plus 1 is equal to the fiber of fi as full time categories of En. So note that such a collection of functors is the same thing as a functor from exit of Gn to stable, where Gn is the n spider. This is Gn 1, 2, E1, E2, E3. Right. The exit path category of this guy is one vertex and edges, and so you have one category in the middle and n categories at the side and n restriction maps. And so these functors define such a constructible sheaf on the n spider. And then these are some conditions.
Do you have some subscripts, superscript on the V or?
The v it's n. Yeah, in principle I can drop the superscript. It has no specific meaning.
Okay, it's not like a product.
No. Okay, that's a further shower on the n spider. And then definition. It's the same definition as with the gentle sheaf. A gentle sheaf was a sheaf, such that on every n spider it's a gentle sheaf. So let f from exit of g be stable. It's called shower, covered shower. That's shower if for all n variant vertices V with corresponding fully faithful inclusion exit of Gn includes fully faithfully exit of G F restricted to exit of Gn is perverse. If you apply K0 to such a diagram defining a perverse shower, then you will get a perverse sheaf on the surface described in an equivalent way in terms of certain categories of vanishing cycles and nearby cycles and maps between these. We won't get into that.
First definition, equivalent to some special kind of sectorial decomposition with pieces and I and some.
Yes. So there's also a definition for n is equal to 1. It's known as a spherical functor. And all of these steps, so if you have a perverse shower on the disk, can describe it in terms of a perverse shower on the n spider for any n. So all these definitions can be turned into each other. They're all equivalent and they're all the spherical functor. And they're all equivalent to 4 periodic semi-orthogonal decompositions.
But for higher end, there is no equivalent.
The same notion.
Okay.
Yeah.
So there is also equivalent.
Yeah. So by doing stop removal, you get from a shower on the n spider to a shower on the n-1 spider. And there's an inverse to stop removal.
Okay.
So an example or maybe exercise. Show that gentle sheaves are perverse. That gentle sheaves define perverse showers. Maybe about one-valent vertices. One more remark. If you have a one-valent vertex, we have V to B. Then if you have a gentle sheaf, what you get, well, in E you assign D of D per K. But we never said this explicitly, but what you assign to a one-valent vertex as a gentle sheaf, you assign the A0 cover. The A0 cover has no vertices. It's the empty cover, so you assign the 0 prime. So this is what a gentle sheaf assigns to a one-valent vertex, and clearly if these equations, like the adjoint is not fully faithful. So this could never satisfy this definition. So there's a version of this definition which works also for one-valent vertices, but it looks very different. Very interesting. The fully faithfulness only starts at n is equal to 2. Right. So a lot of the things we discussed in this lecture series you can do in this more general context of perverse sheaves. So we had stop removal. We had let me see which part here. So you had, for instance, we associate an object with arcs. You can still do this, and what you use these functors GI. So let me maybe try to convince you why this works similarly. So the key insight here is that the 3 indecomposable objects of the H cover, they come from the 3 edges of the triangle. by taking the left adjoint of restriction to the edge. And so if you have a shoulder, you can similarly take these adjoints, and these equations then tell you that you're still the support of the corresponding section is still described by an arc. If you take, let me draw this. So you have a vertex E, you have E1, E2, E3. This is your ribbon graph. Then we have F shoulder, shoulder. If you take an object n x in say f of E1, and you take f of E from E to E1, well, if you let's take the right adjoint, then we're literally in these equations, and then you apply f of B to EI to it. What do you get? Well, in the case that I is equal to 2, you get x. In the case I is equal to 3, why is this d2?
It's FIGI,
So,
GJ, G1.
Hmm?
It's FIG1.
Right, right. This is G1 and this is F1. So when this needs to be I plus 1, this is I, so you get for I is equal to 3, you get, well, some object which is non-zero. For I is equal to 2, you get 0, and for I is equal to 3, you get 0. So what you get an arc, right? Namely, this arc object. This will be f of E to E1 by the joint of x. And so these curved shortcuts, they have a left-right adjoint symmetry. So if you somehow impose the dual conditions, where you place right adjoint by left adjoints, instead of I plus 1, you write I minus 1, they're also true. So if you compute f of E to EI equals to the f of from E to E1, left adjoint of x, you will get x question mark on 0 and something 0. So I is equal to 1, I is equal to 2, I is equal to 3. So you would get the right turning path. And now you simply you now don't know what x is. X is not simply k or shift of k. And question mark is it's some object in an equivalent category obtained from applying an equivalence of categories to x. This equivalence of categories being exactly this composite. You can now simply glue these sections together again in a more general setting where you always remember which objects you have and with the same construction.
Should one understand this like for every given x, you have now like a family of like string objects that you will have in the general algebra, but instead of case, it's just x's, something like this.
Right. Yeah. The string objects. So for a given string, the corresponding object in the topological Fukaya categories are parameterized by z in the possible gradings of the string, and they correspond exactly to the indecomposable objects in the derived category of the field.
So is it also like you can take the your progression over the value in k, and then tensor something like this object to get this object? Can you put something like this? For like globalization.
If your shoulder is somehow just given by a general sheaf tensored with something else, then yes. But general shoulders will be more general form. So I'll remark where examples of shoulders come from at the end. Let me maybe now state the induction results. So proposition. This is in a preprint from September. F is a G parameterized ruler. E and H of G. Then the evaluation factor are gamma GF. F of D admits left endpoint. Mapping each X in f of E to a global section, whose support is given by is described by gamma E right here. You'll see one thing noted that if you have an arc object, the support of the corresponding global section, meaning the edges of the ribbon graph where the section evaluates non-trivially, is exactly described by this curve. So the same will be true here. If you take a fraction, you get a global section, and you can think of it as living along this curve. And the same is also true for if you look at induction from vertices. But what happens there? So if I, where's my color? So if I start at a vertex, I can also ask what happens if I take the induction. In the case of general algebras, nothing will happen because all objects from vertices already come from an edge. So it's kind of a trivial question to ask in that context. But here, now there will in general be objects that vertices which don't come from edges. And then you're taking the branch arc, starting at the vertex and always going right. And induction from vertices, branch arcs. Let's call them webs. And so this representation theory of arcs, kind of very well understood. For instance, intersections correspond to homs. Similar results hold also in this general language of Pavlov-Schobers, because all the arguments you use to prove that in the general sheaf setting were all very formal, and they only used these equations basically, and the theory of time extension. So the same proofs in the general sheaf case will also prove that, say, if you have arc objects of a general Schober, the homs are count intersections. And then for these more general branched arcs, these webs, some of the representation theory is not at all developed. And a very interesting problem to develop this representation theory. And this comes up, for instance, in categorifications of just algebra structures related with higher attachment theory and triangulated categories of theory. So one last comment about Pavlov-Schobers. So how this theory was conceived, and this is not at all obvious from these definitions, is by connection with Pika-Lefschetz theory and the computations of Fukaya categories. So when you have one thing these Pavlov-Schobers can do for you is to compute Fukaya categories as global sections, but not necessarily of the surface. But say you have a symplectic manifold fibered over a surface, then you can find a Pavlov-Schober on that surface, which is more interesting than a gentle sheaf, but it will still satisfy these equations, and its global sections will describe the Fukaya category of the big guy with the fibration. And essentially, this is a consequence of the Ganot-Rapaden-Schende co-sheaf descent properties of Fukaya categories. So yeah, this is, I think, where I want to end my talk. Thank you.
I have a question.
Yeah.
So to a Schober, can you associate it's like kind of a gentle sheaf whose its support?
So not exactly. So oftentimes you can somehow look at the maximal gentle sheaf quotient of your Pavlov-Schober.
Okay. And this will be a gentle sheaf.
Well, gentle sheaf valued in some, it's not necessarily valued in the derived category of the field. Maybe gentle sheaf with coefficients in some stable infinity category.
Okay. So I guess, right, if you take support of your objects, then you will get curves. And curves correspond to objects of the gentle.
But so what's not true in the setting is that all objects come from curves.
Right.
Only a small collection of them will. There are objects corresponding to webs with one branch points or multiple branch points, and this is probably there is more, and it's not kind of, you can't classify for general Schober the global sections.
even these objects are sometimes weighted by another object of their coefficients, right?
Absolutely, yeah.
So
Yeah.
you cannot specify it and you don't much.
More questions? Then maybe I have another.
Mhm.
So maybe more to a lecture which you could have given. So like with those like the right turning curves.
Yes.
Right. So I mean the objects. Okay, the objects know the direction of the curve, right? And then of the Fukaya category.
Well, yeah, you choose
Right.
the wrapping direction, either clockwise or counterclockwise.
Right. And then I mean if you compute, so this arcom is supposed to be computed by intersection, right? And then the intersection kind of you need to remember the direction of the curves you can compute.
Well, the direction of the curve is more relevant for the grading.
But I mean here, so like I mean this proposition geometrically should I interpret it as okay, if I have a right turning arc and I have any other arc on the surface, then the only place they can intersect is at the beginning of the right turning arc. Is this
Yes. So there's a geometric statement like this, exactly. So if I have a right intersections of any arc with a right turning arc, are exactly intersections of that arc with this edge. And if you have a boundary arc, so if you start an external edge and you take the right turning arc, then another arc can intersect this arc if and only if it intersects its start point, basically.
But there E was not necessarily external?
No.
Oh, okay.
No, E is an arbitrary edge.
Oh.
So if you have external edge, you get somehow intrinsic objects to the category. If you choose an internal edge, you get objects that you only can understand with this universal property if you choose a specific ribbon graph. If you choose a different ribbon graph, you somehow get a different collection of induction objects.
But also, is it true for triangulation? If I choose an arc in a triangle,
Yeah.
a right turning arc in a triangle, can I extend it to a right turning arc? I mean, I can, which starts at an external kind of from an external edge.
If you have a right turning arc in.
So if you have a right turning arc,
yeah,
somewhere
yeah,
in a triangle,
yeah,
and then I extend it to a right turning arc,
yeah,
everywhere, then do I know that this right turning arc comes from a mark point?
Mark point.
Or
so,
like
I mean, what it means for an arc to be right turning depends on your choice of triangulation. If you choose a different triangulation, you will get a different
kind.
Yeah,
I think it's a triangulation.
Right.
And I choose a right arc.
Yes, right.
And then I extend it to a right turning. Like
if you have an arc and then you extend it right turning, this means that you're basically taking induction from a subsurface or subgraph to the. So that you can also play the same game where you take any subgraph of your ribbon graph and then look at restriction of global sections to sections supported on that graph, or not supported sections on that graph, and then this also has an adjoint and has a similar description. And basically, what you would do is you would have an arc doing something, and then as soon as you leave your subsurface, you're always right turning.
Oh, sure.
And yeah, then you get similar induction functors for subsurfaces.
Okay, but right. So maybe I'm in like towards like the description of simple objects. So will those right turning arcs? So extension will be somehow. And are they simple objects? Are they like? Will you generate the whole category from the right turning arcs?
I mean, if you every arc is a right turning arc for triangulation.
So you need to go through all triangles.
Yes, absolutely.